Shannon Matchick-Myers, and today we'll continue section 3.1, which covers how to use linear models, linear differential equations, to model applications. So the next couple of examples relate to Newton's law of cooling, so I'll put them together. These will be examples 3 and 4 from 3.1. So first off, just a more basic, a thermometer is taken from an inside room to the outside, where the air temperature is 5 degrees Fahrenheit. After 1 minute, the temperature reads 55 degrees, and after 5 minutes, it reads 30 degrees. What is the initial temperature of the inside room? So, here we go. Newton's law of cooling in general, if you look back at section 1.3, you might want to have those notes with you, goes something like this. The derivative with respect to time of our temperature, right, is equal to some constant times the temperature T minus the temperature, the ambient temperature, right? So with this one, our ambient temperature is 5 degrees, so that's coming from over here. Air temperature is 5 degrees, that'll be our ambient temperature. So we might as well go ahead and you can either, get your equation in terms of the ambient temperature, but you might as well plug in the 5 for 5 degrees. So dt, so the capital T is temperature, would be K times T. I'm distributing the K through, and I'm also putting in the 5 for 5 degrees. And we'll get minus 5 times K. And these are in Fahrenheit. And then I need to get the term that has a T on the left side. So that's going to end up giving me negative K times T. That'll help me get my integrating factor. And that's equal to negative 5K. So to find the integrating factor, I take the coefficient of the T term and have e to the integral of that with respect to time in this case. So this is going to give me e to the negative kt. That negative k is just treated like a constant. And then multiplying both sides by e to the negative kt, I'll have my setup done. And we'll have d dt of e to the negative kt times t. So again, if you look at differentiating what's inside the parentheses I just put in, you would get the same thing that you see with when you multiply that e to the negative kt through on the left. So that's going to equal to negative 5k e to the negative k times t. And then setting it up for integration, we'll have e to the negative kt dt is equal to negative 5k e to the negative k t for time with respect to time. Now I'm looking here and I'm looking at what I need, the derivative using that of negative kt is negative k, so I have that available to use. So when I integrate both sides, I'll have e to the negative kt on the left side times t is equal to 5e to the negative kt plus some constant. So this one, since it wasn't equal to 0, we can't say that it's the initial amount or the initial temperature. So we'll just have that plus C. Now, okay, we now want to multiply both sides by e to the positive kt to isolate that T for temperature. And when we do so, we'll have T is equal to 5, because e to the negative kt times e to the positive kt is 1. And then plus C e to the kt. And then again, if you want to write that at the temperature at time t, you can do so. We have quite a bit of information, but we need to find our k and we need to find our c. So let's take a look at the ordered pairs that we have. So we have an ordered pair over here. After 1 minute, sorry, the thermometer reads 55 degrees. So we have an ordered pair at 1, 55. So that means that T at 1 equals 55. So we can set that up as 55 equals 5 plus CE to the K times 1. We also have this one over here. It was after 5 minutes, it reads 30 degrees. So we have the ordered pair of 530. So T at 5 is 30. So I would say 30 equals 5 plus CE to the K times 5. Cool so far? So now I can work a little bit more with these. If I subtract 5 from both sides, I get 25 is CE to the 5K. And for the other one, 50 is equal to CE to the K. And then working with both of them, I would have 50 is to 25 as CE to the K is to CE to the 5K. So these divide out to be 2. The C's divide out, and I will get 2 is equal to e to the negative 4K. And natural log 2 would equal to natural log e to the negative 4K, which will just be negative 4K. And isolating K will have negative natural log 2 over 4. Cool so far? All right, so now let's take a look at next steps. So we have our K. Now we want to find the initial temperature of the room, the initial temperature, so at time 0. So let's take a look at what to do now. So to find the initial temperature, so for this one, we're finding K. So now let's find C. So we take our temperature at time t equals CE, oh, we had a 5 there, sorry. 5 plus CE to the KT, right? And K was negative natural log at 2 over 4 times T. So I'll use the ordered pair of 530 to find C. So 30 equals 5 plus CE to the negative natural log at 2 over 4 times 5. 25 will be CE to the negative 5 natural log at 2 over 4. So then, taking out our calculator, we'll have 25, I'm going to multiply it by e to the positive 5 times natural log at 2 divided by 4, and we get approximately 59.46. So C is approximately 59.46. And then if you were to round it earlier, you might have gotten 59.4611. This is fine. This is more close to the real. So now what do we have? We now have T at T is equal to 5 plus 59.46 e to the negative natural log at 2 over 4 times t. So now we can find, finally, the initial temperature, the initial temp. So initial temp, we would just let T be 0. So T at 0 would be 5 plus 59.46 e to the negative natural log at 2 over 4 times 0. So T at 0 will be 5 plus 59.46. And that initial temp then will be approximately 64 point, we'll just go to the nearest tenth, 64.5 degrees Fahrenheit is that initial temp. Cool, cool? All right, so another application, which if you watch CSI at all, you might like, is, okay, a dead body was found within a closed room of a house where the temperature was a constant 70 degrees Fahrenheit. At the time of discovery, the core temperature of the body was determined to be 70 degrees Fahrenheit. 1 hour later, a second measurement showed that the core temperature of the body was 85 degrees Fahrenheit. We're going to assume that the time of death corresponds to T is 0 and that the core temperature at that time was 98.6 degrees Fahrenheit. Determine how many hours elapsed before the body was found. So, whoops, sorry, I'm missing we're going to let T1 denote the time that the body was discovered, T1. So, let's check it out. It's the same formula. It's Newton's law of cooling. So, we're still going to use dt dt is equal to, and then remember that formula was K times the varying temperature minus the ambient temperature. So K times capital T minus Tm. Well, in this case, Tm is 70 degrees, right? So we'll have the instantaneous rate of change of the temperature with respect to time will be K times T minus K times 70 degrees. So that temperature, ambient temperature was 70 degrees. So now I need to have my term with the T in it on the left. So dt dt plus a negative K, easier to get the constant, the integration factor that way, will equal to negative 70K. So our integrating factor, really similar to the other problem, it just gets a little weird at the end, is going to be the e raised to the integral of negative k dt, which is e to the negative kt. So multiplying both sides by e to the negative kt, e to the negative kt, what's going to happen? Well, we'll have d dt of e to the negative kt times t equals negative 70k e to the negative kt. Cool so far? All right, so in this one, we will work with this a little bit to get it in the form we can integrate. So e to the negative kt dt is equal to negative 70 ke to the negative kt dt. So again, on this one, if u was equal to negative kt, du would be negative k dt. So we have what we need for our du, negative k dt. Sorry, negative k dt. So here we go, integrating both sides. On the left side, we'll have e to the negative kt times t for temperature is equal to 70 e to the negative kt plus our constant of integration. And then multiplying both sides by e to the positive kt to isolate that t for temperature, we will have t is equal to 70, because those the e to the negative kt and e to the kt become 1, plus ce to the kt. Good so far? All right. So now, here we go. We need to go through and we need to find out, we want to find out the temperature that, the body was. But we are assuming that the initial temperature is equal to 98.6. So again, if we write this at t at time t, that might be easier. So this was just starting to find the general formula, right? So to find C for this one, it's a little easier because we have the ordered pair 0, 98.6. So T at 0 will be 70 plus CE to the K times 0. But what was T at 0? We said 98.6 is going to be 70 plus C. And then when I subtract, I'll get 28.6 is equal to C. Cool so far? So then, now, let's keep it going. I'm going to go ahead and add a page to this one. So now, what do we have? We want to find the temperature of the body that the body was when it was found. So if we go ahead and we let, T1 be the body's temperature, when it was found, and that means that T1 plus 1 would be the temperature 1 hour later. And we were given the ordered pairs, right? So we were given that time of discovery, at the time of discovery, the core temperature was 70 degrees Fahrenheit. You know what? My apologies. I have a typo here. This is supposed to be 85. It wouldn't make sense, right, for the temperature to go up past, because the ambient temperature is 70. So 85. So we have the ordered pair T1, comma, 85. And then an hour later, sorry, again, an hour later it was 80 degrees. And so 1 hour later the temperature was, so we'd have T1 plus 1 and 80. So working with these two, and we have C, right? So we're working with, remember we have T at time T is equal to 70 plus 28.6 e to the kt. So here we go. T at T1 equals 85 degrees. So we have 85 is equal to 70 plus 28.6 e to the k times T1. So this would be 15 is equal to 28.6 e to the k times T1. And now the second one will be T at T1 plus 1 will be equal to 80. So 80 equals 70 plus 28.6 e to the k times T1 plus 1, which will be 10 equals 28.6 e to the kt1 plus k. So now comparing these two, like we've done in the past, we'll have 15 is to 10 as 28.6 e to the kt1 is 2, 28.6 e to the kt1 plus k. So simplifying, this is going to be 1.5, the 28.6's will divide out, e to the kt1 minus kt1 minus k ends up being e to the negative k. Evaluating the natural log of both sides, we'll get natural log 1.5 is negative k, or negative natural log 1.5 is k. Finding that on our screen here. So we get negative 0.4055 approximately. Good so far? Perfect. Now we need to go through and use one of the ordered pairs to find, or actually one of the ordered pairs to go ahead and find our, our next measure here. So I'm going to use this one here, all right? So using 15 equals 28.6 e to the k, which is negative 0.4055 T1, I would have over 28.6 equals e to the negative 0.4055 T1, and then finding the natural log of both sides, we would have this one here. And remember, T1 is the temperature that was the temperature when the body was found. That's why we use this one. And then bringing our deal out again, we'll find natural log of 15 divided by 28.6. And then do you see we're going to divide by that whole thing by negative 0.4055. So T1 is approximately 1.6 hours, right? So what does that mean? Approximately 1.6 hours passed before the body was found. That's pretty quick, huh? All right. Well, that was a little bit about Newton's law of cooling. I hope you had a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe, hit that like button. Bye.